Signals and Systems, Jet Transforms, Part 2, Transform Pairs, Series on Signals and Systems, Lecture number 6.12. Jet Transforms. They are most general transforms capable of transforming sequences, discrete time signals from time domain into frequency domain. Here, in these transforms, frequency is a complex one. Its symbol is Z. It is related to real frequency through Z equal to R e power j omega. These are somewhat similar to Laplace transforms. In Laplace transforms also, transform variable is a complex quantity, a complex frequency indicated by S. S is also, like Z, is related to real frequency through S is equal to sigma plus j omega. In the present session, the focus is on determining the Z transforms for certain standard sequences or signals like delta, Kronecker delta, impulse, step, sequence, sinusoidal, and so on and so forth. We go to finding transforms after recollecting the defining relations of Z transforms and touching upon important points pertaining to ROC of Z transforms. Now, let us move further to begin the core session. Here, the definition of Z transform, corresponding relations, they are all given. The Z transform can be defined as either one-sided or two-sided transform. So, two types of transforms: one-sided or unilateral transform, two-sided or bilateral transform. Bilateral transform of a sequence x of n. Usually it is indicated as x of z. By definition, x of z is equal to sigma n equal to minus infinity to plus infinity x of n z power minus n. This is bilateral transform. Unilateral transform is very much similar to bilateral except for one difference. In case of unilateral transforms, the summation starts from n equal to 0 instead of minus infinity. Inverse transform is also exists. It can be determined from the relation given here, x of n, which is original sequence. It can be determined from the transform x of z using the relation x of n is equal to 1 by 2 pi j, closed line integral x of z, z power n minus 1 dz. So first two are to obtain Z transform. Third one is to obtain sequence, original sequence from which transforms are obtained or for which transforms are obtained. One or two points are mentioned here. In case of Z transforms, transform variable is indicated by Z. and it is a complex quantity equal to R e power j omega. J omega stands for real frequency or magnitude. Z power minus 1 or 1 by Z. It is called delay operator, unit delay operator, whereas Z is called unit advance operator. We use this terminology in the discussion in the study of jet transforms. For that reason, these two are being mentioned here. Now we consider ROC. What is ROC? What is the importance of ROC? What are significant properties of ROC? All those things are mentioned in this slide as well as in the next slide too. First, what is ROC? ROC is the range of variation of Z for which Z transform converges. We can notice from the definition defining relation of Z transform of a sequence. Z transform is basically a summation sigma n minus infinity or 0 to infinity. It is summation. The summation may converge, may not converge. And for certain values of Z, it may converge. For certain values of Z, some other values of Z, it may not converge. So the range of variation of Z, range of values of Z for which the transform converges, that range is called ROC, region of convergence. ROC of Z transform, it is indicated with a circle in Z plane. Z plane is a complex plane. ROC appears like a circle in the Z plane. ROC does not contain any poles. These are all properties of ROC. ROC is a circle, and within the circle there exists no poles. If x of n is a finite duration causal sequence or right-sided sequence, then ROC is the entire Z plane except Z equal to 0. If x of n, the sequence, is a finite duration anti-causal sequence, that is left-sided sequence, then ROC is the entire Z plane except Z is infinity. Z tends to infinity. If x of n is a infinite duration causal sequence, ROC is the exterior of the circle with the radius a. Here mod Z, magnitude of Z is more than a. If the sequence x of n is an infinite duration anti-causal sequence, ROC is inside of the circle with the radius a. It is Z magnitude is less than a. If x of n is a finite duration two-sided sequence, then ROC is entire Z plane except Z equal to 0 and Z tends to infinity. Here in these two slides, this slide and the previous slide, one can find a connection between sequence, nature of sequence, and the ROC. Once these points are in our minds, we can easily know and understand without any calculations the ROC of a sequence. Now let us move further and consider some signals, standard signals, common signals to find their Z transforms. We begin with the delta function. Kronecker delta. Delta of n. Its jet transform can be found equal to 1. ROC is all z, means entire jet plane, all values of jet. How to get, how to find the validity of this result? For that, apply jet transform definition to delta of n. It gives us sigma n equal to minus infinity to plus infinity delta of n multiplied by z power minus n. This is equal to 1. As it is 1, ROC is entire jet plane. Another signal, important signal, common signal, standard signal, that is unit step sequence. Its transform can be found from applying the definition of jet transform to u of n. Here it is given that it is equal to 1 by 1 minus z power minus 1. Now let us see how this relation has come. Jet transform of u of n is equal to sigma n equal to minus infinity to plus infinity u of n z power minus n. It is equal to sigma n equal to 0 to infinity. Notice the change in the lower limit. Earlier it is minus infinity, now it is 0. Reason is step function. It is 0 on the negative time side. Therefore, minus infinity up to 0, the product is 0. U of n z power minus n is 0. Therefore, summation needs to be from 0 to infinity. Another aspect is on positive time side, step function is, or step sequence is 1. So u of n z power minus n becomes simply z power minus n. Now this is written as sigma n equal to 0 to infinity z power minus 1 power n. Using the formula 1 plus x square plus x cube etc. is equal to 1 over 1 minus x when mod x is less than 1. Transform of u of n, which we have seen earlier as equal to sigma n 0 to infinity z power minus 1 power n, becomes 1 over 1 minus z power minus 1. As the summation sigma n equal to 0 to infinity z power minus 1 power n converges only when z power minus 1 is less than 1 or z is mod z is more than 1. ROC is magnitude of z is more than 1. Another signal. This is also a step sequence, but here it is negative step and shifted step, time shifted step. The jet transform of minus u of minus n minus 1 can be found equal to 1 over 1 minus z power minus 1. To find its validity, apply jet transform, defining relation of jet transform to the given sequence. It is equal to sigma n equal to minus infinity to plus infinity minus u of minus n minus 1 multiplied by z power minus n. This can be expressed as minus sigma n equal to minus 1 to minus infinity z power minus n equal to minus sigma m equal to 1 to infinity z power m, with minus n replaced by m. Using the formula x plus x square plus x cube plus etc. is equal to x over 1 minus x when mod x is less than 1. This is the formula. One can write the transform of the given sequence minus u of minus n minus 1 minus sigma m equal to 1 to infinity z power m, which is equal to minus z by 1 minus z, which is equal to 1 over 1 minus z power minus 1. Now we consider another sequence alpha power n u of n. Its transform can be found equal to 1 by 1 minus alpha z power minus 1. Same transform is given by another signal minus alpha power n u of minus n minus 1. Notice transforms are same, but the sequences are different here. To know the validity of the transforms, first we consider the transform of alpha power n u of n. To proceed further, consider jet transform of u of n. We know it is equal to 1 over 1 minus z power minus 1 or inverse z. Now, using the scaling property of jet transform of alpha power n x of equal to x of z by alpha. This is scaling property. One can write z transform of alpha power n u of n equal to z of u of n with z equal to z by alpha, resulting in transform of alpha power n u of n is equal to 1 over 1 minus alpha z power minus 1. In a similar manner, one can also find the transform of minus alpha power n u of minus n minus 1 as 1 over 1 minus alpha z power minus 1. Another sequence n u of n. Its z transform can be found equal to z power minus 1 by 1 minus z power minus 1 whole square. To find its validity using the z domain differentiation problem, transform of n x of n equal to minus z d by dz x of z. This is differentiation property, z domain differentiation property. If we apply this property to n u of n, its transform becomes equal to minus z d by dz z transform of u of n. Of course, it is equal to 1 over 1 minus z power minus 1. Ultimately, we have z transform of n u of n equal to z power minus 1 divided by 1 minus z power minus 1 square. Now, another sequence n alpha power n u of n. Its transform can be found equal to alpha z power minus 1 divided by 1 minus alpha z power minus 1 square. Same transform is there for another sequence minus n alpha power n u of minus n minus 1. So both the sequences, they are giving same transform. To know the validity of these two transform pairs, let us consider the first sequence n alpha power n u of n. Apply z transform. It is equal to minus z d by dz z transform of alpha power n u of n. See, this particular equality has come from differentiation property, z domain differentiation property. And the same thing can be written as minus z d by dz 1 over 1 minus alpha z power minus 1. This relation has come from z transform of alpha power n u of n is equal to 1 over 1 minus alpha z power minus 1. One can do the differentiation to get the z transform of sequence n alpha power n u of n as alpha z power minus 1 by 1 minus alpha z power minus 1 whole square. In a similar manner, it can be proved that z transform of minus n alpha power n u of minus n minus 1 also equal to alpha z power minus 1 divided by 1 minus alpha z power minus 1 whole square. We consider another pair of signals, sequences. Cos omega naught n u of n, sin omega naught n u of n. For cos, transform is 1 minus z power minus 1 cos omega naught divided by 1 minus 2 z power minus 1 cos omega naught plus z power minus 2. For sine, the transform is z power minus 1 sine omega naught divided by 1 minus 2 z power minus 1 cos omega naught plus z power minus 2. We consider sine and try to determine its z transform. Z transform of sine omega naught n u of n is equal to sigma n equal to minus infinity to plus infinity sine omega naught n u of n z power minus n. This is defining relation. It becomes equal to sigma n equal to 0 to infinity. U of n is there, which is 0 on a negative time side. So we need not add from infinity to 0. 0 to infinity. Addition is more than what is required. So it becomes sigma n equal to 0 to infinity sine omega naught n multiplied by z power minus n. It becomes equal to sigma n equal to 0 to infinity e power j omega naught n minus e power minus j omega naught n by 2j z power minus n. Here what we have done is sine is expressed in terms of exponentials using Euler's theorem or Euler's identity, and then they are manipulated a little bit. After manipulation and some kind of simplification, we get the transform as z power minus 1 sine omega naught by 1 minus 2 z power minus 1 cos omega naught plus z minus 2 power minus 2. In a similar manner, it can be shown that z transform of cos omega naught n u of n as 1 minus z power minus 1 cos omega naught by 1 minus 2 z power minus 1 cos omega naught plus z power minus 2. With this, we come to the end of this session. Before closing down the session, let us recollect important topics that are touched upon in the present session. After giving the defining relations of jet transforms, properties of ROC pertaining to jet transforms, they are given, and then we considered, we derived, we have gone deep into the derivations of jet transforms of common standard signals like delta, step, sine, etc. Hope this session is useful to you. We meet again soon in another session with a new topic.